I started the recording. All right, everyone. So good evening. Welcome to our second review for Math 132. This is a departmental mock final. In other words, the sample final, your instructors probably already went over that with you. And of course, I went over that on Saturday morning. I'm sorry, I went over that on Saturday morning. That video is already on our YouTube page. So maybe not tonight, but probably tomorrow in the morning, we will have the recordings for this video as well for our mock final. So here I'm going to look over similar problems that are related to what you might actually see on the final. Okay? So let's begin with the very first problem, right? Very first problem covers some basic definitions. For example, experimental versus observational, sample versus population, statistic versus parameter, and what's wrong with your study. Okay, so in problem 1, it states that in a survey of 1,020 adults in the United States, 94% said they washed their hands after riding public transportation based on data from KC research. I don't know what KC stands for. Maybe keep clean, keep change. I don't know. Keep change flip, keep change change. I don't know. KC research. So it states determine whether the study is experimental or observational. Identify the sample and population. Is the value 94% a statistic or parameter? And then identify a major problem. That might be true. It might be Kansas City, Edwin. You might be right, but I don't know. I'm thinking it might be keep clean research. I don't know. Okay, so let's answer part A. What do you guys think? When you reread that sentence, do you think it's going to be an experimental or observational study?
Observational.
That's right. It's an observational study. The reason why it's observational is that you can use the definition of observation, right? Is the researchers applying any treatment onto these adults?
No.
No, the research is basically not applying any treatments. They're not doing any modification. So the reasoning to this is that the researcher, whoever is conducting the study, KC namely, researcher does not attempt to modify the individuals involved in this study. All right, so that's part A. It's observational. The researcher does not attempt to modify the individuals involved in the study, right? There's no treatment being applied. There's no different groups being created here. One getting treatment, other getting, like, let's say, a placebo. None of that's happened. Okay, so part B now states to identify your sample and population. So let me ask you this question. Which set will always be larger, your sample or your population?
Population.
That's right, the population is always larger than the sample, right? So note, the population is always larger than the sample. Okay, population is always larger than the sample. So we have to figure out what is the population, and then we could figure out what's the sample. So what do you think is your population, or what is your sample?
All adults.
That's right. The population, one of the key terms when you define a population is you use the word all. So it's going to be all the adults, but namely not all the adults in the world. It'll be all the adults in the US. All adults in the US. Okay? All the adults in the United States. However, what would be your sample?
94%.
Careful.
120.
Not
Yeah,
100.
120. No, 1,020.
There you go, 1,020. So it's all right. It's a long day. So the sample is going to be the 1,020 adults in the US, and that's it. So the population, again, is always larger than the sample, but just note that when you talk about a population, depending on the audience, depending on what's being studied, you typically refer to it as saying all, and then the object or individuals of study. Okay, the sample is always a subset of the population. All right, so we have our population, we have our sample. Now, part C states, is the value 94% a statistic or a parameter? Well, if we reread this problem, it says, in a survey of 1,020 adults in the United States, 94% said they washed their hands after riding public transportation. So if you want to answer this question, you basically, the answer to it is answering another question. Who is they in the statement? Who is they?
The 1,020 adults.
That's right. That's right. The they in this problem refers to the 1,020 adults in the US, right? It's basically referring to your sample, right? Our sample is the 1,020 adults in the US. So therefore, in part C, 94% must be
Statistics.
a statistic. There you go. So to really answer this question, you got to answer another question. You want, when you read these phrases, when they talk about a percentage, such as the 94%, who are they referring to? Like, for example, who's the they in the they in this problem? Well, the they is the 1,020 adults in the sample, which is our sample. So therefore, it's a statistic, 94%. Okay, so we got part C done. Now, part D is to identify a major problem with this study. So to answer this part of the question is a little bit different now from the original sample, right? This is a different way of asking you part D. So what do you think is a major problem with this study? A major problem. That's right, Tatiana. The study has some bias. It seems one-sided. Can we clarify? Why do we think that the study is biased? Why do you think it's one-sided? There's actually two logical reasons to this. Well, one of them is logical. The other one, it's based on the wording of this problem.
I'm gonna take a guess. Maybe it's because they chose to ride the public transportation.
Not really. Not really. No, not because they only asked 1,020 people.
Because only 94 answers, so not everybody answered.
Yeah, what about kids, elder people, and more people? It's just they just talking about adults.
No, adults is fine. Adults is fine in this study.
They might lie.
They might lie. That's right. That's right. They might lie. For example, the adults, here's one reason why it could be biased, right? So there is potential to be biased, and there's two reasons why. There is a potential for biasness. One reason, I'll put the first reason here. The first reason is that the people, the adults, can be ashamed to tell the truth about their unhealthy habits, right? I think we've probably seen this sometimes when you use a public restroom. Sometimes you can just see somebody walk out from the public restroom and they don't even wash their hands. So the adults, one reasoning that I could think of is that the adults is ashamed, they're embarrassed. The adults is ashamed to tell the truth. Because if you think about it, if you say that you didn't wash your hand, right, after riding public transportation, then essentially people just they feel embarrassed. They can feel embarrassed about the situation. Think about using the bathroom. You going back to the bathroom example. If you did a survey and you said, the survey was like, do you wash your hands after you use the bathroom? And some people say no, then you get frowned upon. People look at you weird. Okay, so that's one reason why. There's a second reason why. So going back to this KC research, let's say that this KC research, this KC, by the way, this KC stands for keep clean. Keep clean. Why would there be a potential for bias if the research comes from a company called Keep Clean? Let's say that this company Keep Clean, is like a, one of their items that they sell as a business is probably soap, hand soap, or sanitizer. Why do you think there's a potential for bias if this company name was Keep Clean?
Because we don't know if these people are actually washing their hands.
Nope, not quite. Again, think about the scenario. Let's say the company name was Keep Clean, and that they sell the product, right? Product they sell are hand soap, hand sanitizer. Oops, spelled soap wrong. Hand sanitizer.
They want to promote the fact that they're like their products.
Yeah, they want to promote their product, right? Basically, it's a business, so you want to promote your product, right? You're trying to maximize your revenue. So the second potential biasness here is that it's in the best interest for the company because of their own creed, their own interests. Okay, so it's unreliable, namely the source, because of its own creed. Its own creed, right? Their own motives. Their motive is to, like Fanny pointed out, to promote their products, right? This problem, however, for this question, you cannot necessarily say voluntary response. Why? Because if you look at this problem, it is said that these adults chose to respond. No, they didn't choose to respond. They were just, I mean, it's sort of weird, the scenario, because it's like, it wasn't like an opinion poll. It wasn't like an online survey. It could have been something where it was like convenience sampling. So I could agree where you're coming from with voluntary response, but for it to be a major problem, you would have to, in the wording of the problem, it has to say that the sample members chose to respond to the question. Okay, it didn't say it here, so we can't use it. Is there any questions about problem number 1?
No.
No.
Yeah. for C, it's saying is the value 94% a statistic or parameter? Can you tell me what parameter means one more time?
A parameter is a numerical value that describes a population. So, for example, if we knew that the population of the population is all the adults in the U.S., and we run some inferential statistics, and we found that the population's proportion was 84%, just throwing a random percentage. If we say that 84% of all adults in the U.S. Wash their hands after riding public transportation, then that would have been a parameter because it's referring to the population.
So I have to look for the word all, like when.
Yeah, like, if it's talking about a parameter, you would look for the word all. In particular, I mentioned that if you're answering this question, what you should look for is when it says a percentage of they or percentage of people, who are these people that they're referring to? Who are these individuals? So in this problem, the they is referring to the sample, the 1,020 adults in the US. So therefore, that's why it's a statistic.
Thank you.
You're welcome. Any other questions? We're okay to move on?
Yeah.
All right.
Yeah.
Let's keep going. So here's problem number 2 now. Problem number 2 states an engineer is designing a machine to manufacture gloves, and she obtains the following sample of hand lengths, okay? Hand lengths, which is measured in millimeters. That's the unit, millimeters, of 12 randomly selected adult males. Find the 5-number summary for the data, and then is the data discrete or continuous? So when you do the 5-number summary, right, just giving you guys some notes. Oh, my bad, meant to put 5 first. 5-number summary. It consists of 5 things. It consists of, first, the minimum value, the smallest value of your data set. It consists of quartile 1, quartile 2, quartile 3, and the maximum. So the minimum and maximum, they're of course going to be the smallest and largest values. For Q1, Q2, and Q3, those quartiles, let me define them. So the way that I define this is that you first got to find Q2. Okay, Q2, after you find the min and max, you go and find Q2. So Q2 is the median of the entire data set. Okay. Now, because you get Q2 is at the median of the entire data set, it's the halfway point. That's another way of saying it. The halfway point, the 50% mark of your data set. And because it's going to be the value that represents the 50% mark of your data set, then half of the values are less than Q2, and the other half of the values are bigger than Q2. So once you get to Q2, which is the median of the entire data set, you can then find Q1 and then Q3. Q1 is the median of the lower half. Median of the lower half. Q3, on the other hand, is going to be the median of the upper half. Median of the upper half. Annie, yes, you're allowed to use a calculator. You're allowed to use your calculator.
Oh, gotcha. Because there's a way that we could do this in the calculator.
Don't get me wrong, Annie. For almost all the problems that are on this exam, there's a way to do it in the calculators, but that's not my job tonight. My job is to go over the concepts. Once we go over the concepts, and I show you how to do the by hand stuff, then later on, if you want to learn the calculator methods, that's totally fine. Okay. My bad. So I should have mentioned that as well, that everything that I'm doing tonight is strictly by hand methods, where of course, yeah, we use the calculator, but we don't use certain commands from the calculator. We just do computation. We do arithmetic computations. Okay. So we have our 5-number summary. Now, the good thing is if you look at your numbers, if necessary, you have to put your numbers in order from lowest to highest. But just by inspection here, you can see that these numbers are already from lowest to highest. So you can go ahead and already find the min and max, right? So first you find your min and max. Well, what is the minimum value?
158.
158. And your maximum value is going to be what?
214.
214.
214. That's right. You have 158 and you have 214. So the only things that are missing now are Q1, Q2, and Q3. What I recommend that you do first is get Q2. Q2 is the 50% mark. It separates the bottom half from the top half. So to get Q2, we say that it's equal to the median of the entire data set. So again, I'm just going to write that in instead of me writing out all the numbers, I'm just going to say median, and then in parentheses, I'll say entire data set. So let me ask you this question. How many data values are there? How many data values are there?
12.
There's 12, right? The problem tells you that the sample consists of 12 randomly selected adult males, namely their hand lengths. So yes, it's 12. Now, 12, is it an even or odd number?
Even.
Even.
It's an even number. So because 12 is even, then when you want to find the median of this data set, then you have to take an average of the two middle values. So what are the two middle values in my data set?
198 and 202.
That's right. Your two middle values are going to be 198 and 202. So we'll have 198 plus 202 divided by 2. So if you work out the arithmetic, you do 198 plus 202 first. That will be what?
400.
400. And then 400 divided by 2?
200.
200. So here's what I recommend. You start labeling things based off of your numbers. So we have 158 is the minimum. I'll call that the min. We got 214 is the max. And now 200 is Q2. Now, if you look at your data set, is 200 there?
No.
No. But it should go directly in the middle of what two values?
198 and 202.
So right between this 198 and 202, I'm drawing this vertical line. That vertical line is exactly Q2. It's going to be 200. And the good thing about drawing that vertical line is that, again, by its definition, it's the halfway point of your data set. So it separates this bottom half now from the top half. So you can easily identify your bottom half. You can easily identify the top half. And it makes finding Q1 and Q3 much easier now, right? So look, your Q1 now is going to equal to the median of this bottom half that I keep saying. So what numbers are in this bottom half?
It would be 158 all the way to 198.
There you go. It'll be 158, 173, 179, 195, 196, and 198. So again, how many numbers I have?
You're right, Q1. It's Q2.
Say it again.
You're right, Q1. It's Q2.
No, it's Q1.
Why? You put me in.
That's right.
Jesus. Okay.
I said that we find Q2 first, and then we find Q1. Okay. So if you look at Q1 as the median of our bottom half, so how many values are in this bottom half?
6.
6. So your median here should be?
Between 179 and 195.
There you go. You got it. You're getting it. So 179 plus 195 divided by 2. So what's 179 plus 195? You add that up and then divide that by 2. So let me know what you got. Sorry, I probably cut you off.
187.
187?
Professor, can you repeat that, please?
Oh, we're just taking the median of, we're just taking the average of 179 plus 195 divided by 2. So those two values, when you add them up, then divided by 2 gives you 187. 187. Okay, good. So let me ask you this question. Is 187 on my list?
No.
No. So you can informally, you can draw another line between 179 and 195 to show that, okay, here's my Q1. It's 187. All right. So there's only one thing missing, and that's Q3. Well, to find Q3 by our method is the median of the upper half. So I take the median of the numbers that are involved in the upper half. So where does the upper half begin? At what value?
202.
202. So you begin at 202, and you go all the way up to 214. Okay, so how many values are here? There's, again, 6 values. So you need to take the average of the 2 middle values, which is 207 and 210. So when I add them up and then divide by 2, let me know what you get.
208.5.
There you go, 208.5. So that value will be located here. Is there any questions? So in ascending order, your 5-number summary is 158, 187, 200, 208.5, and 214. One of the follow-up questions to this is that if your professor asks you for a box plot, just saying if they ask for a box plot, the way that the box plot will look like is the following. You see how I have my 5 numbers implemented, where you can clearly see it in my data set? From that data set, you can clearly just draw a quick box plot. Check this out. I could draw my box. Can everybody see my box?
Yeah.
Yeah, and then you just draw the whisker parts, right? So from what I just did there, that's your box plot. I just got to put it on a number line, right? So your box plot looks something like this. Let's say here's my number line. Let's say that on my number line, I start at 150 instead, and I went up by, let's say I started at 150, but I went up by 10. So let's say here's 160, here's 170, here's 180, 190, 200, 210, and then let's say over here will be the 220 mark. You plot your numbers, right? So 158 is close to 160. 187 should be close to 190. 200 is at the 200 mark. 208.5 is close to 210, and then 214 is somewhere in the middle between 210 and 220. So you draw your box that goes around the Q1 and Q3 values. My box didn't came out nice, that's okay. You draw a vertical line that goes through Q2, and you just draw the whisker parts. And that's your box plot. Okay, so we're almost done with this problem. The last thing the problem asks is if your variable, your data, is discrete or continuous. Okay, so that's the last thing that this problem asks, if your data set is discrete or continuous. So we're gonna answer it. The way that you answer discrete or continuous is as follows. You think about the following phrases or words. When you say discrete, the data set is basically countable. It contains data that takes on specific values. Whereas continuous is the opposite of being discrete, right? So you say it's uncountable or you say that it's measurable. It's measurable, right? Like temperature. Temperature is measurable, so it's continuous data. So measurable means that data takes on any value in an interval. So let's look back at our data set here. What was our data set talking about? For example, the numbers 158 all the way to 214, it represents what type of numbers?
It was talking about hand sizes, like measurements?
Millimeters.
Yeah, it's a hand size, the hand lengths, right? So in this problem, our data, oh, my bad. I know I show off the MS3 logo, but I wasn't trying to show it off that much. But our data here was the hand sizes, the hand lengths, which were given as units as millimeters. So is hand lengths going to be discrete or continuous?
Continuous.
Discrete.
It's going to be continuous.
Continuous.
Right? Oops, spelled that wrong. Continuous. Why is the data set continuous? Well, look at hand lengths.
Because
Is
it's a
hand lengths-
measurement.
It's a measurement. That's right. If you look at this problem, it gives you the units that we involve. And anytime you involve some sort of units like millimeters, inches, feet, minutes, hours, it's some sort of measurement. So therefore, it's continuous data. The way that you can decipher that also from discrete is that usually, if you're talking about countable things, you can count it off your fingers. And if you count it off the fingers, the phrases usually begins with number of. Like if it said the number of, I don't know, the number of gloves manufactured per day, number of gloves manufactured, then that's discrete. Because you can count the number of gloves that are being manufactured per day, right? However, if you're talking about some sort of measurement now of these gloves, like the hand lengths, you're looking at measurable data sets, so it's continuous. Any questions? We're all good on the 5-number summary and the second part to this problem?
I have a question.
Go for it.
So only when the randomly selected adults is even, like the number, that's when you add like the two middle numbers to get like the median?
Oh yeah, absolutely. If your data set consists of only even numbers, then the median to get it, you have to divide it by 2. Take the average of the two middle values. So it happened that, you see, if you cut 12 in half, right? Because we had 12 data values. What's 12 divided by 2?
6.
There's 6. Right, so if you notice, there's 6 values on it. It's going to be on the left and 6 values on the right of Q2. And because of that, then when you have to find Q1 and Q3, then you have to take the medians, where again, you take the average of the two middle values for both cases. Because again, there's 6 values in the bottom half. There's 6 values in the top half. Okay? If you had 10 data values, then if you cut 10 in half or divide that by 2, it's 5. So that means 5 values would have been in the bottom, 5 values would have been on the top. If that was the case, then the Q1, Q3s would have been precisely the middle value because, again, 5, the number 5, is an odd number. Anytime it's an odd number, your medians are always just the middle value. Sounds good, Mr. Rosario?
Yes, thank you.
You're welcome. Anybody else? Questions?
So, Professor, so in that case, we wouldn't divide, we just take the middle value.
Wait, say it again?
So in that case, we wouldn't divide by 2, we just take the middle value. If it's
That's right.
anytime
Anytime you have odd numbers, like 1, 3, 5, 7, 9, middle value, that's it. Anything even, 2, 4, 6, 8, 10, or 2, 4, 6, 8, ending with 0, you gotta divide by 2. Are we all good?
Yeah.
Okie dokes. Let's look at problem number 3. Problem number 3 states, consider the scatter plot given below. Which of the following values could be the value of R? So you have 5 choices. So here's a little quick, oops, my bad. Here's a quick number line to break down R. So I talked about this during our last time we met on Saturday, but I'll talk about it like we never met. So when you look at the value of R, it's always between what two numbers? The two values that are always between R is always between is -1 and +1. All right, so R is always between these two values, and the middle of -1 and 1 is 0. So what I'll do here is include some more numbers. I'm going to put 0.3 on this side, and I'm going to put 0.7 on this side, and then I'll put -0.3 here, and then I'll put -0.7 here. Okay, so if the correlations are perfect, if the linear correlations are perfect, then R must be -1 and 1, which is not the case here, because if I just drew a line that starts from the first point all the way to the last point, you can see that all the points don't fall on this line. So therefore, R is not going to be -1 and 1. But more importantly, if R is negative, then what type of correlations do we have? Positive ones or negative ones? If R is negative.
Positive?
No, not quite. If R is negative,
Negative ones.
you'll have negative correlations. And because you'll have negative correlations, that means that the line should be decreasing. Okay, so if you have anything that's between -1 to 0, it's negative, whereas anything from 0 to 1, it's positive correlations. The line is increasing. So looking at your values of R, and then looking at this line I drew, do you think I have a positive correlation or a negative one?
Positive. Positive.
It's definitely going to be a positive one. So which values of R can I eliminate?
The negative one.
Yeah, get rid of the negative ones. Okay, so now we have to just break down what type of positive number it could be. Well, it depends on the correlation, right? So not only you can say that the correlation is negative or positive, but you can say that there's a strong one, it's a moderate, or it's weak. So it's strong, it's really strong if it's between -1 to -7, -0.7, or 0.7 to 1. We say that it's moderate if it's between the 0.3s to 0.7, and we say that it's weak if it's anything between the -3 to +3. Okay, there's weak or no correlation. So at 0, there's none. Okay, so what do you think here? You have 3 choices. Do you think it's a weak, moderate, or strong correlation? We already know it's positive. But do we think it's
strong? It's strong.
It looks strong, right? This looks like a strong positive. So because it's strong positive, then I know that the value of R must be between 0.7 to 1. So what two values here are not between 0.7 to 1?
0.231
Uh-huh.
and 0.555.
That's right. So the only possible choice we have for R is 0.981. Right? So
Can you repeat that one more time on how we got 0.981?
Oh, because it's a strong positive correlation. You see, R, if it's strong positive, based on the wording here that we describe it, then R must be between 0.7 to 1. 0.981 is somewhere in that number line, somewhere right around here. So it indicates that we have a strong positive, and that's the case. That is the case. Okay, now we move on to part B. Part B says to write the equation of a regression line. So if you want to write your equation of the regression line, want to write your equation of the regression line, you use the following equation, right? So this equation that I'm going to write for part B is no different from what you probably saw in high school. It's called y hat equals b1 times x plus b naught, where b1 is the same thing as saying m. And in high school, what do you learn that m stands for?
Slow.
A slope. M stands for slope. And b naught is simply the y. I'll give this one away. It's the we call this our y-intercept. Okay, that's basically your b. B naught is y-intercept, which in you know the linear equation y equals mx plus b is the y-intercept. Okay. Okay, so in this problem, did it give us the slope?
Yeah.
Yes.
Yes. Did it give us the y-intercept?
Yes.
Yes.
It did. So you just got to plug them in. Just plug them in. So for B1, we got 1.888 x times x, right? So y hat is equal to 1.88 times x plus, in parentheses, the y-intercept, which is negative 0.645. Okay, negative, sorry, I'll write that a little bigger. Negative 0.645. Okay, you can simplify your equation a tad bit here. You see, anytime I have a positive and a negative next to each other, what does a positive and a negative make? Do they make a positive or a negative?
A
Negative.
A negative. So just to rewrite this equation, it's 1.888x minus 0.645. And that's it. That's all part B asks you to do. Nothing more, but just to write an equation of the regression line. Now, in part C, once you have the equation of your regression line, part C asks you to use the regression line to predict the y value for when x is equal to 4.55. So x is like a predictor, right? You plug in this value of x to make a prediction. You're trying to figure out what would be the y value. So when x is equal to 1.88, sorry, not 1.88, I was looking at that number. X was 4.55. I plug that in to my equation, and then I solve for y hat. So we get 1.888 times 4.55 minus the 0.645. So you multiply the two numbers first, you get a result. Once you get a result, you then subtract by 0.645. So if you do this, can somebody can I have a volunteer? Can you try this out? Let me know what you get when you work this out. Yeah, Tim, you worked it out for me?
I think so.
Okay,
Is
you
it,
can give me an answer without rounding.
Okay. 7.9454.
Okay, 7.9454. That's the exact answer we get. But if we had to round this, let's say to just 3 decimal places, you'll say 7.945 because the 4 at the end tells the 5 to stay the same. So this would have been the solution to problem 3. 7.945. Yeah, there's no 6. The 6 was just a number on the slide, so I just got rid of it. But there you go. Any questions?
We round only if it is x.
That's a good question. It depends on what the professor say. So if I say 3, then round 3. If your professor say round 2, then you round 2. Okay?
Yeah.
So just be careful. It's just like when you do the MyLab homework, right? Sometimes you get the right answer, and then you put it in, you get it wrong. But the reason why you get it wrong is because you got to round to how many decimal places they say. Okay, so just pay attention to that. Be alert to how many decimal places needed to round. Yeah, Tim?
So I'm not entirely sure if this would be on Lady Lakich's final, but just to clarify, for B, or for the answer for part B, when find the slope intercept equation of the regression line is just the y equals 1.88x minus 0.645.
That's right. Y hat is the same thing as Y.
Okay,
That's right.
got it. Thanks, Anthony.
You're welcome. I'm just showing the notations that students will see that in the My Lab. It's just notations. It's just the language. Anybody else? Any questions? To be very honest with everyone, I do not see how you can get these three problems wrong. The first three. I think the very first three problems, you should get them right. Just make sure you just read the wording, right? When I get to the later problems, you also obviously have to read them, but just make sure you look over what you're being asked to solve for, okay? All right, we can move on to problem 4.
Yes.
Okie dokes. So problem 4 now, we start getting into probability. It says a car dealership sells 3 types of cars. We call them X, Y, and Z. And any of these 3 models can be fitted with automatic or manual gearbox. The data is shown below, okay? If one car is selected at random, what is the probability that the car is type Y or automatic? If one car is selected at random, what is the probability that the car is manual, given that the car is type Z? Okay, so for part A, what is the key word when solving this probability?
Or?
The word or. And what probability rule comes to mind when you hear of the word or?
Addition.
Addition, that's right. So when you hear about the word or, you refer to the addition rule. So the addition rule, it states the probability of A or B, the probability of the first event or the probability of the second event is equal to the probability of A, your first event, plus the probability of the second event occurring, minus the probability of both A and B. Okay, sometimes you have to avoid double counting. So let's look at our A and B. So for part A, we have type A, type Y, and automatic. So your type Y is essentially your A, automatic is essentially your B. You substitute it into your formula. Just substitute it, right? You have the probability of type Y or automatic. Well, this is going to equal to the probability of selecting a car that's type Y plus the probability of selecting a car with the automatic gearbox minus the probability of type Y and automatic. So type Y and automatic, you could just simplify that as saying the word both, right? It contains both characteristic. All right, so because I'm computing probabilities based off of my table, you write these values as fractions, you do some computation with them as fractions, then round at the very end. So don't round anything yet, round till the very end. So if I'm selecting a type Y car, what is the probability of selecting a type Y car?
Would it be 56?
Well, there are 56 type Ys. That's not incorrect. Okay. There are 56 type Ys. But we gotta write it as a probability. So it's 56 over what?
120.
120. It's 56 divided by the total number of cars, which is 120. All right. Now, how many cars are automatic?
100, but don't we have to subtract 44 to not duplicate?
We're gonna get there. I didn't get there yet, but we will. We will.
Okay.
44.
No, not 44. How many automatics are there?
100 out of 120.
Yep, there's 100 automatic cars, right? So I didn't get to the both part yet. I didn't get to the ending. I only got to the second part, the middle part. There's 100 automatic cars out of the 120. Now, where it says the minus both, that's where you minus off the any intersection. Is there an intersection between the type Y and the automatic? And if so, how many cars are in that intersection?
Would it be 44?
Now it's going to be the 44. Okay, now it makes sense to say 44, right? This is basically 44 cars that are both automatic and type Y. All right, so because we have these numbers written, these probabilities written as fractions, it makes computing them, I don't want to say simple, but makes it easy for ourselves because you see the denominators are all the same. All you got to worry about is just adding and subtracting the top numbers, and you leave the bottom alone. So what is 56? So I'll write it this way so you can see it. 56 plus 100 minus 44, all divided by the 120. So now you can work this out. What's 56 plus 100?
156.
156. And if you subtract that by 44, that would be what?
112.
112. So we get 112 over 120. That is a good answer. But now you can round this answer to 3 decimal places if it asks you. So if you round this answer to 3 decimal places, what do you get?
0.933.
0.933. Very good. And that is your solution. Okay? That would be it for problem part A of this problem. Now, here's a case where you could sort of like make sense of your answer, right? Let's do a what if scenario. Just a quick what if scenario, because this might happen to some students. Might, because of nervousness, whatever the case may be. Let's just say I didn't put this minus 44. Let's just say I didn't put this. Let's just say I only put 56 plus 100 divided by 120. Well, 56 plus 100, we established that earlier as 156. If I have 156 over 120, can this represent a probability?
No.
No. Why can 156 over 120 not represent a probability?
It will be
It
bigger
would
than
be
1.
greater than 1.
It will be greater than 1. It will be greater than 1, right? So this here is a big no, can't happen because it's bigger than 1. Probabilities, they measure the likeliness of something happening. So probabilities are always between 0 and 1. Okay, so if you see that you get any answer that involves, finding the probability of something, and you see that you get an answer that's, again, bigger than 1, that's a big red flag there. Probabilities cannot be greater than 1. Okay. All right, now that I established that for part A, let's talk about part B. So part B states if one car is now selected at random, what is the probability that the car is manual? Car is manual, given that the car is type Z. So what is the key word when you read part B? The key word.
Given.
Given, that's right. My bad, my internet might be a little bit unstable, so if you don't hear me clearly, let me know and I'll repeat myself. So the key word here is given. This refers to conditional probability. And conditional probability has this fancy notation. It says the probability of B, use this bar to represent the word given. Okay, so this bar, this vertical bar, is the word given. Right? The probability that the second event occurs given that the first event already occurred. So I mentioned last time, for the folks that were here last time, I mentioned a way where you can sort of do this informally rather than using a strict formula. And the way that this works is that you always compute the bottom number first. Somebody asked me if I have like a sheet of the keywords for the probabilities. Unfortunately, no, I don't. But for number 4, you need to know or and conditional probability. You need to know or and conditional probability. So what I'm writing here is what you need to know as the formulas and the keyword. Okay, so the way that I do this is I always figure out the bottom number first, which is the number of ways in favor of A, of whatever A is, your first event. So it should be like more like saying the number of outcomes in favor of A. But ways work here too. The top number now you figure out second, right? So it's like you go bottom up. Number of ways in favor of A. The top number is now what we say the number of ways in favor of A and B. Basically A and B happening somewhat simultaneously, so that's an informal way of thinking about it. But what this formula is really saying is, okay, depending on what happens with A, what will be the number of outcomes of B? Again, depending on what happens with A. So here's how this works. Looking at the way that part B is written, you could define what B and A are. B always comes before the word given. It's always the second event. So that second event is the word manual. The first event is the word type Z. So if you want to do part B, just setting this up for us, you get the probability using the notation, probability of manual, that the car is manual, given that the car is type Z. So I go bottom up. I first figure out how many cars are type Z. And then out of that many cars that are type Z, how many of them now are going to be manual? So let's look. How many type Z cars do we have?
38.
Right, 38. Right, you look down into the type Z's, the type Z's row, column. So we get 38. The big number there was the 38 on the bottom. Now, out of this 38 cars, how many of them are manual?
5.
5. So that's it. You write it as a fraction. Out of the 38 cars that are manual, 5 of them are now manual, right? So we write it out. We say 5 over 38. And that's it. You write this now as a fraction if you wanted to. Like, let's say if I wanted to round this to 4 decimal places. If I round this to, let's say, 4 decimal places, hypothetically speaking, what would you get?
0.1316.
0.1316. And that'll be your answer. That's it. Always find the bottom number first, and then figure out what's the top number. Okay? Now, if I wrote 38 over 5, what's wrong with that?
It will be more than 1.
It'll be more than 1, which is no good. Okay? You can't have probabilities that's more than 1. Let's do another quick example of this. Okay, so part B, the answer was 5 out of 38. It was 0.1316. But I just want to go back to the table real quick so I could just throw another example. Let's say I did a part C. Let's say I wrote out the probability notation for us. Let's say we want to do probability that the car is type X, given that the car is automatic. Okay, so type X given that the car is automatic. Well, what should I figure out first? The number of type X cars or the number of automatic cars?
Automatic.
The automatics, that's right. So how many automatic cars are there?
100.
There's 100. Now, out of that 100 automatic cars, how many of them are type X?
23.
23. 23. And then you write this out as a decimal, you get 0.23. So that ain't bad. Okay. Any questions? We're all good? Feeling better with the probability of problem 4?
Yes.
Okay, let's go on to problem number 5 now. So problem number 5 states in a survey of randomly selected adults, I did a lot of examples with randomly selected adults. 78% said they were worried about identity theft. Okay. 78% said they were worried about identity theft. If 10 adults are selected at random, find the probability that at least 9 adults are worried about identity theft. So problem 5 is what type of example? What type of probability formula I'm going to use? What's the name of it?
Binomial.
It's a binomial. That's right. It's a binomial probability. And the formula for binomial probability is as follows. We say the probability of x, whatever x is going to equal to n choose x times p to the x power times q to the n minus x. So let me define these variables for us. Let me define them. We make some replacements, and I show you how the computation works. So let's start off with n. Let's start off with n. What does n represent?
The number of trials.
10 adults.
N would be the number of trials or objects. So in this case, you could say number of trial objects. That's fine. Here, with the objects or the trials or the individuals are the 10 people. 10 people were randomly selected. Okay, good. Now, what does X stand for? What does it represent? I don't want to with the numerical value of X, but I rather
At least 9.
we call it at least 9. But why do we call it at least 9? What does it represent? Or what does it mean?
At least 9.
No, not at least 9. Just what does X mean? How does the textbook or your class defines X?
Isn't it like
Number of successes?
Yes.
That's right. It's the number of successes amongst the n trials. Okay. So don't get me wrong. At least 9 is X, but I just want you to just define why it's at least 9. And the reason why it's at least 9 is because of the fact that it's the number of successes amongst n trials. Okay, so if X is the number of successes amongst n trials, in this problem, X is at least 9. Now, when you think about at least 9, let's interpret it now. At least 9 means what? Somebody said it earlier.
9 or more?
9 or more. Well, it can't be 9 or more in the sense where it goes all the way up to infinity. It will have a stopping point. So what are the values of X? Well, we start with 9. X is equal to 9. And X will equal to what other value?
10.
10. You see, if X was equal to, N was equal to, let's say 15, if N was equal to 15, then we would have had 9, 10, 11, 12, 13, 14, 15. But that wasn't the case here. You only go up to n trials. So if n was 10, then you only have to go from 9 and 10. Now, because we have two values of x, then how many times are we going to use this formula?
2 times.
We're going to have to use the formula 2 times, right? So because there's two values of x, I'm just going to write that here. Since there's two values of x, that means we use the formula twice. I have to use it twice because there's two different values of x. All right, now let's talk about what's p and q, and then we're ready for the computation stuff. So how do we define p in class or in your class?
Probability?
No, it won't be a problem. Well, the little p, not the big P. The little one.
Success rate.
The success rate. I'm sorry to confuse you. Yeah, because it was two different P's. The big P is the probability, yes, but the little p is the success rate. That's what I meant to ask you, so I'm sorry. Little p is the success rate of any given trial. So what is your success rate in this problem?
0.78.
It was the 78%, which is the 0.78. And now, what is Q?
Isn't that like the failure? So 1 minus.
Yeah, that's a failure. So it's 1 minus P. So if P is 0.78, you do 1, minus 0.78, which is, what? One minus 0.78 is a very important number.
22.
There you go.
0.22.
There you go. 22 is a very important number for Raphael. Just throwing that out there. Okay. So we have P and we have Q. Now let's do the computation. So this problem asks us to find big P, the probability of at least 9, right? Probability of at least 9. So this is equal to the probability that x is equal to 9 plus the probability that x is equal to 10. Okay, probability that x is equal to 9 plus the probability of x equals 10. I have to use the formula 2 times because there were two values of x. So I'll come back to this. I'll put a line here. I'll come back to this. And let's just do the computation separately. So if I want to do the probability of x equals 9, then this is equal to 10 choose 9 times p, the value of p, which was 0.78 raised to the power of 9, because that was x, times q, which was 0.22 raised to the power of n minus x, right? Don't forget there's an n minus x and the exponent for q. So if n was 10 and x was 9, then that would be to the first power, right? 10 minus 9 is 1. Okay, so now let me show you how to compute the 10 choose 9 part. So 10 choose 9 is equivalent to saying 10 factorial over 9 factorial times 10 minus 9 factorial. So you can compute 10 choose 9 with the calculator. Some calculators allow you to compute it, but you can do this by hand as well. If you look at your denominator, what's 10 minus 9?
1.
1.
So if you know your factorials, which factorial is bigger in the denominator? 9 factorial or 1 factorial?
9.
It's 9 factorial. So the numerator, you could rewrite this as 10 times 9 factorial divided by 9 factorial times 1 factorial. But the 1 factorial is just the number 1. Okay. Now, if you look at the numerator and denominator, they both contain a 9 factorial, so you can get rid of it. You're left with 10 times 10 divided by 1, which is 10. So your numerator, when you want to compute the probability of x, x is equal to 9, this is going to be 10 times 0.78 raised to the 9th power times 0.22 raised to the first power, which is just going to be 0.22, right? Any number raised to the first power is just that number. Okay, so if I multiply all of that out into my calculator, right? Can somebody just give me the first 5 decimal numbers you see? The very first 5 decimals.
How much are we rounding it to?
Just 5 for now.
It would be 0.23511.
Mm-hmm. 0.23511. Okay, so that's the first probability. Now we do the second one. So if you have probability that x is equal to 10, you just got to insert these things back into the formula. Okay, so this is going to be 10 choose 10 times 0.78 to the 10th power times 0.22. Well, remember, you have to subtract n minus x to get your exponent. So what's n minus, what's 10 minus 10?
1.
Careful.
0.
0. But don't worry, I know why you said 1. Because if you have any number raised, to the 0 power, that number is always
1.
1. That's always going to be 1. Okay, so now all I got to worry about is what's the 10 choose 10 part, and then I'll multiply things out. So 10 choose 10 now, 10 choose 10 is equal to 10 factorial over 10 factorial times 10 minus 10 factorial. But what's 10 minus 10?
0.
0. So this is equal to 10 factorial over 10 factorial times 0 factorial. What is 0 factorial? There's a special rule. What's 0 factorial?
Wouldn't it always be 1?
It's always going to be 1, right? So because that's always going to be 1, that just goes away. And since it goes away, you only have to worry about what's 10 factorial over itself. Well, think about it. If 10 factorial is a number, if I take a number divided by itself, then that's always equal to
1.
1. That's right. So 10 choose 10 is 1, right? There's only 10. If there's 10 people and I'm selecting all 10 of them, then there's only one way of selecting them when order doesn't matter. So 10 choose 10 is just 1. Okay, so when you multiply this all out, it's just really multiplying. Just take computing 0.78 to the 10th power. So what is 0.78 to the 10th power when you round this to now 5 decimals?
So would it be 0.08336?
0.08336. I'll take your word for it. I don't want to pull up a calculator at the moment. I'll take your word for it. All right. So we have our 5 decimal points. So now we're going to add these two numbers together. So I take this number and I take this number and I'm going to add them. So this is going to be equal to 0.23511 plus 0.08336. So when I add these two values, let me know what I get.
.31847.
0.31847. And because sometimes the problem might ask you to round to 4 decimal places, now you can round this final answer to 4 decimal places and you can get 0.3185. And that would be your final answer. Put a smiley face. You can use a calculator method for this. If you have a graphing calculator like the TI-84s, But you could ask my class. We typically do these problems by hand. So that's why I show it by hand. But if your professor shows you how to do this in a calculator, just typing in buttons, then by all means do it that way. But unfortunately, I don't know it. I don't know it off my head, those commands. But if you do, you should get something relatively close to what I have, 0.3185. All right. Any questions? Yeah, sure, Jada. I'll just go back up. So here I just defined everything in the first slide. If you notice, I label out all my values, and then I started doing the computation in the second slide. I recommend all students to do this, by the way, right? Like if you know your formula, write out the values of n, x, p, and q. Because if your instructor is grading your final exam, partial credit will be given. So if you make even a slightest mistake, at least this is reasonable to show me that, hey, you understand some bits of the problem. It's just that when you got to the computation part, you made some, human mistakes. But at least here, this shows me you have conceptual understanding of the problem. So if you were doing this on the exam, my class or any instructors, 132, I recommend that you do it in some format like this. You're welcome. Anybody else? Any other questions? All right. I'm going to do number 6. So starting from number 6, we're going to need the Z table. Now, I don't know if this is going to work, but through Zoom in the chat, I'm going to try to attach. I tried to do this earlier. It didn't work for a student, but I'll try again. If you don't have a copy of your Z table, I'm giving you a formula table that is provided from the textbook, right? So if you click on that file, you should be able to open it. When you open it, you want to go to the Z table. Now, again, I don't know if it will work, but hopefully it does. So that way you can have that Z table. We're going to use the Z table for the next 3 problems, problem 6, 7, and 8. And I'll show you how we are going to use them. Okay. All right. So here's problem 6. Problem 6 contains 2 parts, parts A and a part B. It states, it is reported that the average person uses 123 gallons of water per day with a standard deviation of 21 gallons. Assume the variable is normally distributed. Part A states, find the probability that the average person uses less than 120 gallons of water per day. Part B states, find the probability that the mean for 20 randomly selected is less than 120 gallons of water per day. Okay, so part A and part B are almost similar, just the wording is different, and because the wordings are different, the formulas that you use for part A and part B, namely if you're doing them by hand, the formulas are slightly different. Now, when you read part A, one of the key words here in part A is it says the average person, the average person. So when it says the average person, how many people are they referring to here?
One.
One. The average person refers to one individual, right? So part A, the average person is like saying one individual. Okay. Now, because the variable is normally distributed, what type of graph will I be sketching here?
Bell shape.
A bell shape, okay? So let's say I make my sketch of the bell shape here. So our bell shape that I'm drawing is in terms of the variable x, right? Where x represents the number of gallons of water that a person uses per day, okay? So for this normal bell-shaped curve, the variable x, there's two things that I know about it. First of all, it gives me the mean. What is the mean for this problem?
One twenty three. No,
123.
123. Yeah,
You got it. And the standard deviation?
21.
Mm-hmm. Is 21. Now the mean is located at the center, right in the middle, 123. And this isn't variable x. We're trying to find that the probability that the average person uses less than 120 gallons of water per day. So if you want to sketch this graph appropriately, where is this 120 located? Is it located to the left of your mean, or is it located to the right of the mean?
To the
To the
left.
left.
To the left.
To the
To the
left.
left. That's right. So let's say somewhere here is 120. Now, because it says that it's we want to find a probability that it's less than 120, then I have to shade to the left of 120. Okay, so we got the graph. Now we're gonna start solving for this. If you look at x here, x is in what we want to do here is transform this non-standard variable x in terms of z. Okay, you want to standardize your variable. So when you standardize it, the new mean is going to become 0, and there's going to be a new value for the 120. Right? So for this 120, when you standardize it, let's call that our x1 value, you're going to get a z1 value. I'll call it z1 down here. Now, the thing is, how can I standardize an individual value? Do anybody remember what formula is used to go from x to z?
The C formula.
The z-score formula, that's right. So the z-score formula for part A state that z must be equal to what?
X minus M over the standard deviation.
That's right. The data value of interest, the single individual data value of interest, minus the mean over the standard deviation. So if x is 120, the mean is 123. If I divide that by 21, I get a z-score, right? So let's compute this. What is 120 minus 123 over 21? Well, let's work this out. What's 120 minus 123?
-3.
-3. So you get -3 divided by 7. -3 divided by 21. Now, when you compute this in your calculator, z is like money. Okay, z is like money. You always got to round this to 2 decimal places. So if you round this to 2 decimal places, -3 over 21 becomes
-0.14.
-0.14. All right, so let's write out what I just did here. So I just found out that when x is precisely 120, z1 is approximately -0.14. Now, when you're trying to find probabilities under a probabilities that involve the normal distribution curve, this bell-shaped curve, it's equivalent to finding areas. So I'm going to write the following 2 statements. The first statement was going to be in terms of x, right? Originally, we were trying to find the area to the left of x equals 120. However, this is equivalent now when you transform it in terms of z, in the second statement. It's the same thing as saying area to the left of z equals negative 0.14. There's not much to do after this step. There's not much to do. Here's why. That's right, Sadia, you're going to get 0.4443. The reason why you're going to get that answer, I'm going to write it out. I'll show why. Is that because this problem states that we have, we're finding an area to the left of x or even z. When you use the z-score table, it only gives you the area to the left, right? So let me pull that up. I'll be right back. There we go. So, here we go. Okay, so what was our z value again? I forgot. Negative 0.1, and it ends with 4, right? Negative 0.14. Yeah. So when you go under the z, the first column for z, you begin with negative 0.1. So here it is. It's here all the way on the bottom. It's there on the bottom. And I know that it ends with a 0.04. So when I look at when the row and the column meets, right? So the 0.04, by the way, it comes to the left of that first arrow that you see here. This with the little star. That's the 0.04 column. You look at when that column meets your row. Your column meets your row at precisely 0.443. And because, again, the z-table only gives you the area to the left, then that's it. That's all you have to do. End of story. Boom, you're done. 0.443 is your final answer. Okay. So I'm just going to go back. Oh, wait, we already wrote out that answer, but I still got to go back nonetheless. Okay, so using the z-table, we got this answer. Any questions? Now, why did this work? Why did all of this work? It's because the average person implies one individual, right? Find the probability that one individual uses less than 120 gallons of water per day. That probability will be 0.4443. Typically, I won't fall in this category. Usually in the mornings, when I have to teach my 9 a.m. class, I usually fall asleep in the shower a little bit. When the hot water hits, fall asleep. Happens. All right, so that's part A. Now we do part B. Part B states find the probability that the mean for 20 randomly selected is less than 120 gallons of water per day. So my question is this: when we do part B now, is the 120 or is x equal to 120, or 120 is equal to something else? That's my first question here, right? It said find the probability that the mean for 120 or for 20 randomly selected is less than 120 gallons per water. So is x equal 120, or 120 is equal to something else?
Is this one with the X bar?
You tell me.
It is with the X bar?
That's right. So if it is with the X bar, should X be 120 here?
No.
No, right? So it is not X equals 120, but 120 is equal to something else. That something else is precisely the sample mean, right? In other words, if I randomly selected 20 people, that's going to be the value of n. What is the probability of the 20 randomly people selected that the sample mean is less than 120? So in this problem, the 120 is your X bar. Okay. Now, it's almost the same picture as part A, just a little bit different. And because it's a little bit different, And given that the fact that x is no longer 120, it's x bar equals 120, then the formula changes. The formula changes. So when you do part B, to transform or standardize x bar to z, we use the following formula. We say z is equal to what? Do anybody know what's the formula?
X bar minus the mean divided by the standard deviation divided by the square root of n.
That's right. The standard deviation divided by the square root of n. Okay, so our x bar is 120. That's true. The mean for our population is the mean of the sample means. That's 123. Standard deviation is 21 and n is 20. Okay, so we're going to write this out. We're going to say that for part B, z is equal to 120 minus 123 over standard deviation, which was going back up 21, divided by square root of 20. All right, so 120 minus 123, we already know that's -3, but this bottom might not be a nice number. So you can stop at 5 after the 5th decimal mark, or you could round it to 5 decimals. Try 21 divided by square root of 20 and round that to 5 decimal places. Let me know what you get.
$4.69574.
Let me try that. I probably did this wrong in my calculator. So let's see. 21 divided by the square root of 20. Yeah, oh, I did it wrong. Okay, cool. 4.69574. All right, so the more decimals you use, the better. Right, the more decimals you use, the better. Ruth, I think you should try again. I think you probably did 20 divided by square root of 20. 21 divided by square root of 20. Yeah, I got 4.69574. Okay, so now you take -3 divided by this value. -3 divided by 4.69574. If you round this to 2 decimal places, what do you get?
-0.63.
Well, what came after the 3?
0.63887.
So the 8 tells the 3 to do what?
Converse 4.
Yeah, round it up to 4. You get -0.64. Right? So just remember, z is like money. You always got to round z to 2 decimal places. So what we got for problem 6 is the following. So I'll write this in words. The area, now it's the same type of problem because it said less than, so it's, that's left case. So the area to the left of x bar equals 120 is the same thing as the area to the left of the given z value that we just computed, which was -0.64. And because I'm dealing with the left case, all I gotta do is just look up this on my z table. So I'll be right back. Sadia, you're probably right, but I'm just gonna double check. So the z-value was negative 0.6, and it ends with a 4 again. So negative 0.6 is here. The 0.4, looking at when it matches with the negative 0.6, it meets at 0.2611. So that will be your probability. Your probability is going to be 0.2611. Ruth, you probably got 0.26109 only because you might have used a different z-table. But if you round that value to 4 decimal places, you get 0.2611. All right, so that will be your solution to part B. Is there any questions?
Can you go up?
Sure, I
Just
can go
try.
up.
You said a z-score is always rounded to 2 decimal places, right?
That's right, the z-score value.
Okay.
You round it to 2 decimal places only because when you use the z-table, it only goes up to 2. But if you use like any software like the TI-84s or the Microsoft Excels, it doesn't matter. Z can be more decimal places. It will actually give you a more precise area, but 0.2611 is fair enough. Now, here's my last question. Last question before I move on to problem 7. Why? My question is, why did this formula work? Why? Why could I use this formula? Not because I mentioned it or somebody else mentioned it, but why did it work? For example, how can I tell that the sample means, right? Because we're finding the probability of sample means at the end of the day, right? How can I tell that when I look at the distribution of the sample means, how can I know that this distribution is normal? Well, not because n is 20 and it's less than 30. There's a little bit more to it. You see, if n was greater than 30, then yes, right? Then yes, it's going to look like the graph. It's going to look normal, okay? It's going to look normal if n is greater than 30, but n wasn't 30 here. N was 20. So why did it still work if n was 20?
If the original population is normally distributed,
That's
then the
right.
sample
That's
means.
right. That's right. So there's 2 conditions. If n is greater than 30, then yes, the distribution of the sample means is going to be normally distributed as well. But there's also a second condition. The second condition says if n is less than 30, then the original data must be normal. Okay, the original data must be normal. And if you look back at this problem, did it say that the variable or the original data is normal?
Yes.
Yes, it did. So that's one. There's 2 reasons as to why this work. It has to satisfy one of the criterias. If n is greater than 30, then yes, automatically the formula works because the sample mean distribution is going to be normal. However, if n is less than 30, which was true in this case, n was 20, 20 is less than 30, then the original data must be normal, okay? All right, pretty good. Any questions here?
That one was kind of similar, like one of the quizzes.
That's right. That's right. Okay. We can move on to problem 7. I'm going to move on to problem 7. So problem 7 states, another example of randomly selecting adults. In a survey of 557 randomly selected adults, 284 said they were underpaid. Use a 99% confidence level. So you can thank Raphael, he's in the meeting. You can thank him for this example. This is some data that we pulled up years ago because we were interested about this kind of information. So it states, find the best point estimate, identify the margin of error, E, construct the confidence interval, and then interpret the results, okay? So for each parts A, B, and C, you got to know specific formulas. So if you want to find the best point estimate, your best point estimate is always the sample proportion for a population proportion. So for part A, we have that P hat is equal to X over N, okay? Where, again, P hat represents the sample proportion, and it's the best point estimate of the population proportion. Okay, so if you want to compute this value, you take X divided by N. So what's X over N?
284 over 557.
That's right, 284 over 557. So when you compute this value, you round it to 3 decimal places. 284 divided by 557. This one you can round to 3, Sadia. If you round it to 3, you look at the 8, and then the 8 tells the 9 to do, yep, you got it. You get 0.510. There you go. So that's part A. Part A done. Part A is done. All right, we move on to part B. So part B, you want to compute now the margin of error. Margin of error, we call that, we denote it as the English letter E. So E, the formula says it's Z alpha over 2. Oops, that looked like an infinity symbol. Z alpha over 2 times the square root of P hat times Q hat over N. So this is how we figure out Z alpha over 2, right? So let me define these things, and then we can insert it into the formula. So Z alpha over 2 is just a fancy way of writing the word critical value. All right, Z alpha over 2 is a critical value for a certain confidence level. Okay, Z alpha over 2 is a critical value for a certain confidence level. So if the confidence level, confidence level CL, I'm abbreviated, is 99%, the Z table gives you Z alpha over 2, the critical value. All right, so I'm going to come back. I'm going to come right back. If you look at the Z table here, there's the negative Z scores, and there were the positive Z scores, negative and positive. Now, if you look at the bottom right of this positive, the bottom right, it gives you the common critical values, okay? So on your final exam, the confidence levels that you should see, is 0.9, 0.95, and 0.99, right? That's 90%, 95%, and 99%. So if a confidence level is given to you, like for example, 0.99, then it tells you what the critical value is. That value that you see, that I draw the arrow to, 2.575, is going to be our critical value. Okay, that's going to be the Z alpha over 2. Sounds good?
Yeah.
All right. So again, this is why problem 7 requires the Z table, and that's the only thing you need from it. So Z alpha over 2 is going to be 2.575. All right, we know that P hat, we already compute this, P hat was equal to 0.510. So what would be the value of Q hat?
One minus 0.510.
1 minus 0.510, which is
0.49.
0.49. So I'll write it as 0.49 because 0.510 is just 0.51. All right. Now we know that n is equal to 557. That's right. So I just gotta plug everything now into my formula. Okay. So for part B, we're gonna have E. Oh, my bad. That's the wrong E. That's sigma. Sum. That's not the case. It's E equals the critical value, the 2.575, times the square root of 0.51 times 0.49 over 557. So I recommend that after today's meeting, you go around and you practice this part, finding the square root of this value, and then you multiply it by 2.575. When you get the value of E, you can round it to 3 decimal places. So try it out. Take the square root of 0.51 times 0.49 divided by 557. Do that first. Whatever answer you get, multiply it by 2.575 and round to 3 decimals. Round to 3 decimals. 3 decimals. 3 decimals. Rounded to 3 decimals. What do we get?
0.055.
0.055. So Ruth, I'm not certain what you did in your calculations because obviously I'm not present there. But the correct answer for E should be 0.055. Okay. So you have to do square root of the 0.51 times 0.49 divided by 557, right? So make sure that the division of the 557 is inside of the square root, and then multiply by 2.575. So when you do, you get 0.055. All right, I can write this out real quick. It doesn't take me long. So in the calculator, this is what you should do. In calculator, begin with your square root symbol, right? So you have your square root symbol. Depending on your calculator, you can get that square root symbol. Then you have an open parentheses. So inside of the open parentheses, you get 0.51 times 0.49 divided by 557, and then you close the parentheses. An answer will appear here, right? If you hit enter, then hit enter, you get some answer, right? So I'll put the smiley face here for answer. Then you're going to take that answer, whatever you get, and then you multiply it by 2.575. Now, whatever you get in the calculator, when you round it to 3 decimals, it comes up to 0.055, okay? So this is an answer from the square root part. And then you just, whatever you get, just multiply it by 2.575. No, it won't be 0.0211. Gotta try again. Well, now it's correct, but you see after the 4 is a 5, so you round it up 1. Okay, it's just practice. You got to practice it. On my lab, on Pearson My Lab, where you look back at your examples that you did in class, just practice it. No biggie. Just practice it. Okay, so we did part B. We got the value of E. Now we just got to construct the confidence interval. So the confidence interval states that it's going to be P hat, the sample statistic, which is the sample's proportion, minus the margin of error, is less than P hat plus E. So since P hat, the result of part A, was 0.510, right, we're going to have 0.510 minus the margin of error we just computed, 0.055, is less than P, less than 0.510 plus 0.055. So on one side, you subtract the numbers, and on the other side, you add them. So 0.510 minus 0.055 is what?
Point.
0.455 is less than P, and then 0.510 plus 0.055 is what?
.565.
0.565. So somebody else asking me if this is to find the lower bound and upper bounds. The answer is yes. You see, the 0.455 is your lower bound and 0.565 is the upper bound. So when you want to interpret your results for part D, we say we are 95% confident. Oh, no, sorry. It wasn't 95, it was 99. We are 99% confident that the true value of the population proportion is between 0.455, which is your lower bound, to the 0.565, which is the upper bound. And that's it. That's it. Any questions?
Can you scroll back up to A and B?
Oh, no worries. I'll rotate it. I can't really zoom in that much. I think this is the best I could do with the zoom in for now.
All right, thank you.
You're welcome. Okay. Anybody else? Any questions here? Wait, I don't understand your notation. You said CL is P, hat P is E? No. No. P hat is X over N. E is something else. E, the formula is Z alpha over 2 times the square root of P hat times Q hat over N. The formulas are shown on the screen for parts A and B. But to get the critical value, well, yes, to construct your confidence interval, yes, you need to know P hat and E, but your formulas, the way that you call them there is not correct. That's what I'm implying. Confidence level is equal to P, hat P is E. No, I don't agree with that. I think you probably had your notations a little mixed up. Oh, I think I know what you mean. You see, oh, no. Yes, you mean P is plus or minus. Yes. Yes, that makes sense. P hat plus or minus E. So I'll write it here. This is what you're saying. You're saying that P, you could be 90, whatever your confidence level is. P is equal to P hat plus or minus E. And again, you could be the confidence level, the percentage of it. Yes. Something like that. What I wrote on the bottom. Yeah, that makes sense. Yeah, that makes sense. That makes sense. But what you had originally, it didn't. That's why. I was just looking at their chat. No. But now it does. Now it does. Sorry. It does now. All right. Anybody else? Any questions here? We got one more to go, but any more questions for me here? We're good? We feeling good? Feeling better? All right, one last problem to go. I saved the best for last. That's the one that some of you probably don't like too much. That is the hypotheses testing. So, again, during the sample final, the original sample final, I show you one way of doing it based on the way it's worded. Here's a second way of doing it based on how it's worded. So problem 8 states that a researcher states more than 35% of people drink a caffeinated beverage to combat midday drowsiness. A recent survey found that 25 out of the 52 people stated that they drank a caffeine beverage to combat midday drowsiness. Test the claim at your significance level. Test the claim at your significance level. All right, so this is how we're going to work it out. You have to do this problem essentially in 6 steps. And essentially 6 steps, even though it shows you parts A through D, 4 parts, you do this in 6 steps. Part A, we get 2 of the steps out of the way. Step number 1, you state the null and alternate hypothesis, right? State your null, which we call HO, that's your null, and HA, which stands for alternate. So some professors, they use HA or H1. I just use HA because that helps me distinguish between the two. A stands for alternate. So what is your null hypothesis here? What do you think will be your null?
I think because on 35, I know the 35% is the one that we're gonna use.
Yes, so both null and alternate hypothesis involves a percentage. Now, a percentage, is it a proportion or is it a mean?
P equals 35?
Yes. So for the null hypothesis, we're going to say P is equal to 0.35, right? Because 0.35 is the same thing as 35%. Now, that is my null hypothesis. What is the alternate hypothesis here? It involves P and involves this percentage, 35%. There you go, Sadia. It's going to be greater than. All right, what gives it away that it's greater than 35?
I have a question.
Give me 1 second.
More than.
The word more than. Okay, what's your question?
I don't know if you remember, but I was there, right? I was there yesterday. So how do I know if I have to use P or sigma? Because sometimes we use sigma too.
If it says sigma, then you should see some word that resembles mean or average.
Okay.
Right? So for sigma, use this symbol if you have mean or average, right? That's a population. But we use P because, well, you're given a percentage. You're given part of a whole. So part of a whole is a fraction. You can write as decimals and, of course, percentages. All right, so we have our null and we have our alternate hypothesis. Now, which one of them is the claim? Is it the null that is the claim, or is it the alternate that's the claim?
Can you repeat that?
Is the null the claim or the alternate is the claim? What is the original claim based on this problem? Yeah, HA. HA. Not HO, HA. HA is the original claim. HO is something that we just universally accept as true, or we just assume it's true. Okay, we assume it's true. But HA is the claim. The counter argument to this is that the proportion, the population proportion, is greater than 35%, which is 0.35. Okay, so that's step one. Now, inside of step part A, I'm going to do step 2. Step number 2 is just a quick sketch so that I can refer back to when I get to the decision time, when I get to part C and D. So what we have essentially is a normal distribution. Okay, we have a normal distribution. Jada, it depends on the problem. In this problem, because it says that a researcher states, just to answer your question real quick, Jada, because it says the word states, that's like equivalent to saying claim. So the research is claiming that more than 35%, okay? All right, so here's my quick sketch. First of all, what is our significance level? In other words, what is the value of alpha?
0.05.
0.05. Now, 0.05 should either be an area in the left tail, right tail, or two tails. Depending on the alternate hypothesis, it tells you what type of test is it, what type of test we have. So since the alternate has the greater than symbol, I know it's going to be a right tail test. Okay, so this symbol here tells us that we have a right tail test. And because I have a right tail test, then alpha, our significance level, is going to be the area precisely in the right tail. So here, shading this in real quick, this will be your area in the right tail. So alpha is equal to 0.05. Okay, so this will be helpful now when I get to part C and D. You'll see. So let's go back now to part B. Part B states to identify the test statistic and then round it to 2 decimal places. So, sorry, I gotta mute somebody's mic. There you go. So for part B, the test statistic here, what do you think is gonna be? We have 2 options. For the test statistic, do you think it's going to be Z or T?
T.
C.
It's going to be Z.
Oh shit.
It's going to be Z. Why? Because I told you earlier that we're going to use the Z table for problem 8. No, there's a little bit more backstory to it. But in short, because we're dealing with a proportion, because we're dealing with proportions, you use the Z, a Z test. That's right. It's one population. That's right. So I'm gonna call this Z, our test statistic, Z test. Okay. So the formula states that Z test is equal to P hat minus P over the square root of P times Q divided by N. So let's just figure these things out. You see, I already know what P is. P was equal to 0.35. That was the population proportion. P hat, on the other hand, P hat is going to be X over N, like what we saw in part C, problem 7. So what do you think will be the value of X when you reread problem 8?
25,
Mm-hmm. And Edwin, what's going to be n?
52.
52. So you got 25 over 52. So if you do 25 over 52, you round that to, if needed, you round it to 3 decimal places. 25 over 52. So if you round that to 3 decimal places, what do you get?
0.481.
0.481. So in the numerator, I have to take p hat minus p. So what is p hat minus p? Well, that's going to be precisely 0.481 minus 0.35. So 0.481 minus 0.35 should be what?
0.131.
131. That's right, 0.131. So this is equal to 0.131 on the top. Now it's just to figure out the bottom number. So for your bottom number, we already established that P was 0.35. So what is my Q?
0.65.
0.65, and N of course was 52. So when I take the square root of 0.35 times 0.65 over 52, this one, I want to use as many decimals as I want, so let's just use 5 decimals. I think 5 is fair enough. So in your calculators, you have to compute the square root of the 0.35 times 0.65, and then divide that by 52. So let's say we stop at 5 decimal places. Can I get the 5 decimal numbers?
Point 0.06614.
Angelina, you got to try again. What you're gonna get is 0.6614. Okay. Now you take the 0.131 divided by 0.06614, and this value you can round it to 2 decimal places, since we're computing a z z value. So what do we get if I round this? No, if you do the 0.131 divided by 0.06614, you get approximately 1.98. Okay, good. So the z-test value for part B is 1.98. All right, now we move on to part C, right? So what I did here in part B was step 3, and that was again just computing a test statistic. Part C is where you look at step 4, which you compute now the p-value. In short, the p-value is the area or probability, however you want to word it, probability or area, is the probability or area of your test statistic in the direction of the alternate hypothesis. So look at your alternate hypothesis. We concluded that it is a what type of test?
Right case.
A right tail. So because it's a right tail, the p-value for part C is going to equal to the area to the right of z equals 1.98. Now let me ask you this question. In your z table, does it give us the area in the right tail?
No.
No, it only gives us, well, it doesn't give us the area, not in the right tail, but to the right of a z value. It only gives us the area in which direction?
To the left.
To the left. So if you want to find the area to the right of the z value, you must do what?
1 minus the third.
That's right. 1 minus area to the left of z. Okay. So I look up what that area is from the Z table and subtract it from 1. So I'll be right back. We go back here to our table. We look at the positive Z scores. So I know that we start with 1.9. Here it is. We end with a 0.08. So I look when that column intersects the row. So it intersects at 0.9761. Okay, it meets at 0.9761. Okay, so if I do, going back, 1 minus 0.9761, then when you subtract this, what did you get, Sadia? You got 0.0239. That sounds about right. All right, so that's part C. Now we go on to part D, which is your last 2 steps. You go to step number 5 and step number 6. So step number 5 is the decision time. Step number 6 is your conclusion. Okay, decision and conclusion. Well, we first found out, we just found out from part C rather, that the p-value was 0.0239. The alpha is equal to the significance level, which was 0.05. So look at your p-value. Is it less than or greater than alpha? It's less than, right? So p-value is less than or equal to alpha. So because this is true, p-value is less than or equal to alpha, then what do? Do we reject the null or fail to reject the null?
Reject.
You say that you reject the null hypothesis. So here's our conclusion. You write this out now formally. So our conclusion is that, well, if we reject the null hypothesis, which was that the proportion we assume is equal to 0.35, then there's enough evidence to support your claim, okay? So for your conclusion, you say that there is enough evidence to support the claim, right? The original claim. And that claim was that the proportion, the amount of people that are drinking caffeine is greater than 0.35. So I'll just write this informally. I'll say that the P is greater than 0.35. But because going back to the problem, it's implying that the number of people, the proportion of people that drink caffeine during a midday to battle midday tiredness is going to be greater than 35%. And I think that's true because if you think about finals week coming up, you know, majority of you are probably drinking caffeine in the morning, afternoon, in the night. You're so wired because of these exams coming up or whatever finals you have, papers, you're up all day working. But it will pay off. Hard work does pay off. I believe in that. If we were to fail to reject the null, then there's not enough evidence to support this claim. Hypothetically speaking, yes, that would be true. If for some odd reason we end up saying that the p-value was greater than alpha, then we failed to reject the null. Here's how you can tell. This is why the picture is helpful. If you look at alpha was 0.05, the p-value was 0.0239. So your test statistic, by the way, was 1.98. It's just fancy way of saying these things. It's just fancy way. Whoever's typing in the chat, I can't see the name at the moment. It's just fancy way of saying it. I do it informally. I say it informally because it makes a little bit more sense. But our test statistic, by the way, was 1.98. That was our z-test value. And if you notice, that z-test value is inside of the critical region. And because it's inside of this critical region, it's enough to show why you're rejecting the null. If for some reason the z-test was outside of your critical region, let's say if it was somewhere out here and was outside of your critical region, then it would have been no good. Okay, but that wasn't the case here. All right, everyone, that was the review for today. I'm just going to rotate this so that way if anybody want to see all the steps, what I'm going to do is just stop the recording and answer any more questions.